that calculus has a ton of notation to it. There's just so many. It takes so long to type calculus because it's all math types. Um, go back to a real quick idea. We talked yesterday about how we could find change between 2 points. What do you call that line? A secant line. Way to go. Now that's actually truly how much the y changed and how much the x changed. We also talked yesterday about it, how if you wanted to get really, really close to change at a point, you could take that point closer and closer to this point and get a really close point over here, yeah? You with me? I'll call it a little green triangle, but it's not even visible. Those points are so close together that they almost look like they're on top of each other, right? All right. Now, if I took a magnifying glass to this triangle, then this delta y becomes more of what we call in calculus dy. Now, there were two creators of the calculus. Newton, who was working in England, and he was well established already as a brilliant physicist, so he had some major credit already. There was also this German, lesser-known mathematician in Germany, Leibniz, Gottfried Wilhelm Leibniz, and he did more like this idea. Now, he called these infinitesimals, and he said dy is the smallest positive possible number, to which everybody said, what does that mean? I mean, what is that, 0.1? Well, they're smaller than that. And so there's this huge argument, and they just basically laughed at him for years. This guy created the calculus, and he was mocked mercilessly for most of his life. The idea that you could have this infinitesimally small number that's not negative, that's just barely positive, that's really what dy is. This is a microscopically small delta x and a small, or delta y, sorry, and this is a small delta x. And so together then, the ratio of those dy to dx is, what do we call that opposite to adjacent? We call that tangent, yeah, that's tangent. That's the tangent slope, is dy to dx. So a little bit of rise, dy, and a little bit of run, dx. So a bit of notations, you'll see mixtures in calculus. You'll see Newton's notation, which is function notation, and Leibniz notation. And you need to recognize and be proficient in both and what they mean. So how is this read? F prime at 3, excellent. What does it mean? The derivative at 3. What does it mean graphically? The tangent slope at x equals 3, right? Okay, well, the instantaneous rate of change at x equals 3. They're all the same. What does this mean? F prime of x, and it is the derivative at any x. It's basically a rule that would give you the slope at any point once you told it, hey, at 2, where's the slope? So on, right? Now, here's Leibniz notation, what I didn't get to. This is also the derivative at any x. And it's read, people want to read it as dy over dx as, but it's just read dy dx. You don't read the old ones. Dy dx. Okay? You read that as dy dx, and it is the derivative at any x in Leibniz notation. F prime of x and dy dx are the same. They're just different notations for the same thing. Derivative at some point. In Leibniz notation, if you want to communicate, hey, I don't just want the derivative any old place. I want the derivative at a specific place, then you have this evaluation bar. You draw this bar up and down, and then you say, at what x here? So this, in Leibniz notation, is the derivative at x equals 0. And you would read that as dy dx at 0, or dy dx at x equals 0. You with me? Okay, cool. That should do it. The book sometimes will throw this stuff at you, and that is just terrible. That notation is used for determinants of matrices and cofactor notation with Cramer's rule. just, there's no other textbook that uses that notation. Don't do it. But just so you know what they're asking about. They're asking about that. All right. Are you with me so far? Cool. Looking at, I know I'm a little, oh, this is the wrong one. Did I start recording this? Yeah, okay, cool. I'm a little behind in my grading, and that's got to be frustrating because I do have a quiz for you tomorrow on this. But I'll just say this. Some of you are locked in, you totally understand. Some of you have kind of misconceptions on some things. I'm not sure if you're clear. Actually, I'm not even sure. Did I put the answers to the continuity homework? Uh-oh. Up? I didn't. Are you sure? Are you? I don't believe it. So continuity, more details. And you're right. Okay. Well, no wonder it was so wrong. You didn't have answers. I got you. I apologize already. So that's a problem. It means then that you don't really know if you were doing continuity, but that's not good. I guess I'm going to have to adapt then. Tomorrow's quiz then will be mostly over limits, and we'll leave continuity and IDT so you feel a little more confident, okay? Okay. There were definitely some holes there, and now that clears up a lot. I thought, God, this class doesn't give a rip if they're getting it right or wrong, but now I know why. All right, so I will go over. I did keep track of kind of what you guys don't really have down cold on continuity. I will go back over it over the next couple days. I'll replace some problems, and so you will notice. While we're here, might as well say I replace problems quite a bit. Saxon's great. And most of the problems are super, but I do replace them often to beef them up or give you more practice on some things. So don't freak out about that. I will also say this. Now that you're in the book, you, again, probably will want answers. Yeah, there you go. Okay. I don't take class time to post Saxon answers. I don't have the time to do that. So you will find in the AB Calculus tab, and this looks slightly different when you're on your phone, but it's basically the same setup. In the AB Calculus tab, go into Documents, and you'll see some documents. I had the summer homework and such. The syllabus is there. Here's where you will want to focus. Here's even answers to Saxon even answers 18 to 70. And so you can look at your even answers. And if you're dumb enough to copy them, then you will pay. At this level, I trust that you know how to use the answers effectively. And if you don't know where it's coming from, that you'll ask. Okay? So, for the rest of the semester, you'll be able to find those there. Understood? Okay, cool. Let's go to the next idea. Gosh, that makes me feel so much better about the continuity. You're not terrible at continuity. You just need a little more instruction. Excellent. Let's go to today's notes. This is, you might notice that the problem says 2021. 2021 in the textbook are pre-calculus ideas. And so I'm condensing a little, and I'm actually teaching something that's not even in Set 2021. So I hope you're paying attention, because if you are taking a nap today and then you go to look up Set 20 and 21 in the book tonight, you will not find this. You'll get used to it. It's free. All right, so here's the deal. The alternate and symmetric definitions of the derivative. This will be also a good review of yesterday. Yesterday we talked about the idea of the derivative thing. It's got all these different meanings. It's change rate of change of slope, slope of a point, all these different things. But at its heart, it was taking a change or slope between 2 points and then getting the points closer together by using a limit, right? Now that's true for the other alternate kind of backup definitions of the derivative. There really are 3 definitions of the derivative, what's usually called the definition or the first definition of the derivative, which we talked about yesterday and we'll read here. There's also called the alternate definition and the symmetric definition. And they all have their good and bad. But all of them have that same idea of slope between 2 points, get the points close together. Slope between 2 points, get the points close. It's always that idea that's hard. Really just different kind of ways of getting there. Now, if I take the first definition at x equal a, then I am trying to find the derivative or the change at a specific point. So it's used to find f prime at a certain x value a. Yeah? I use delta x or h. Some books use h as a delta x. I'm just going to stay with what we did yesterday, and maybe eventually I'll use h. H is less writing, honestly, but it doesn't have a lot of meaning. So I'm going to go with delta x. So a plus a little off to the right, which is a change in x, so delta x. You with me? So the slope then between the 2 points would be the change in the y's. So what's the y of this point? F at a plus delta x minus f at the other, which is f at a over delta x. Okay? Now that's the secant slope, or average rate of change between 2 points. We then slap a limit on it to get the points closer and closer together, so it becomes slope at a point. What's the limit we use? The limit as delta x, or the difference between the 2 points, gets smaller and smaller. And then again, the difference quotient. All right. Now, if I then saw something like this, you don't need to write this down because you might not have space, but if I saw something like this, I might say, hey, that's looks like a derivative because it's got some delta x junk in there. And it looks like it's the derivative at a certain number. What number? 2. And it looks like the function, instead of just being some random f, it looks like it's the function of x squared. Right? And so from that, you say, oh, I get what they're doing. All right. So that we'll do that in a second, but we'll come back to that. Now, we also talked about yesterday how you could find, instead of the derivative at a certain point, at any old point in the curve, and get a rule for the slope at any point. That's f prime at any x. In that case, you still need to create a point a little off to the side, so x plus delta x, and draw the slope. Let's bypass the slope thing and just go straight to the whole thing. What is the slope between the 2 points? What's the change in y? Leave a little space here for our limit, okay? Leave a little space there. We're going to write the limit there. But what's the change in y's? What's this y value? F at that x plus delta x minus this y value, f of x over delta x. And how again do I get the points closer together? Delta x goes to 0. All right. So if I had something like the limit as delta x goes to 0 of x plus delta x cubed minus x cubed over delta x, what is it? The derivative of x cubed at any old x, right? All right. All right, let's get to the new stuff. The alternate definition is used to find the derivative at a certain number again. So it's kind of like that first one. I want the derivative at 2. What do you think? Right. Throw that point down. It doesn't really matter where. It could be any point. Now here's the first place it gets a little different. Instead of using this delta x idea to show go off to the side, they just say let this point be any old point on the curve. And any old point on the x-axis we could call x. And if I go up to the curve and draw a line through that, then this point is a, f of a, and this is x, f at x, just any old point on the curve. And so if I wanted to find the slope between the two, what's the slope between the two? What's the change in the y values? F at x minus f at a over the change in the x values. Now this doesn't have a delta x in it, so you actually have to show the difference in the x values. So that is x minus a. It's the difference between the x's. Think y1 minus y2 over x1 minus x2. Algebra 1, right? All right, now, a little different also is that to get the points closer together, the limit is slightly different because, again, there's no delta x here. Instead, I'm just going to say I'm going to move one of the points. Now, which of the points do I move? The x point or the a point? The x point. The x point can change. It's a variable. But a is a constant. It ain't going nowhere. It's constant. It's not moving. And so if I move, I have to move x towards a. If I move x a little closer to a, and a little closer to a, and a little closer to a, well, then I'm starting to get a tangent line. So how do I move x closer to a? X needs to approach a. So for example, if I saw this limit, I may say, well, it could just be a plain old limit problem like we did last week, but it might be a definition of the derivative where the function is x squared, and I'm trying to find the derivative specifically at 2. So this is the alternate definition used to find f prime of 2. All right? And then we could find the limit from 1 to 2. All right, that's alternate. Last but not least, I should be changing colors here because it looks cool. All right, so symmetric. Now, symmetric is kind of kooky, but the idea is, say you wanted the derivative at some point a. Now, all these guys actually use the point you wanted the derivative at, which makes sense. Derivative a is a. But symmetric doesn't even use that. It says in a symmetric way, so same on both sides kind of way, I'm going to take a point a little above. Now this little above, it goes back to that idea. This is a plus a little above. I'm going to use that point, and then I'm going to take a symmetric or same on both sides approach and go a minus delta x, a little below. And I'm going to draw, oops, I missed, the line through those 2 points on either side of my point of interest. And then, rather than move one point like I have been doing, I'm going to move both. So if I make delta x a little smaller, boom, and then a little smaller, boom, and a little smaller, I still am going to approach tangent or slope at one point. So this point is a plus delta x, f at a plus delta x. This is a minus delta x, f at a minus delta x. So in terms of the slope, isn't it f at a plus delta x minus f at a minus delta x for slope between, or change between the y's? And in the bottom, what's the bottom? If you did straight up change in x's, isn't it a plus delta x take away a minus delta x? Well, how does that sound? 2 delta x's. Why is that? Well, does that make sense? Well, sure, it's a delta x on this side and a delta x on that side. So the change in x is 2 delta x's all together. Now, how do I get the limit statement to get the points closer together? X, do I want to take x down a, or do I want to, is it more like those where I take the change or the gap down to nothing? Yeah, it's more like those. I want to take that delta x closer and closer to 0, and when I do that, the change gets closer and closer to 0, and I start to get change. So it's back to the gap being taken to 0. Oui? Okay, now then, let's do a little compare and contrast. Say I wanted to find the derivative of 2 minus x squared at 1. I could do that two ways. I could say I'll use the first definition. You've got to use that actually three ways. I could use the first definition. I'll come back and I forgot to mention something else. Or I could use the alternate definition because they both do derivative at a point. Now if I use the first definition, then that looks something like that, yeah? That's what we learned yesterday. And because we're talking change at a point, I'm using A instead of general f. If I then got into the nitty-gritty, the limit stays. But now, function specific, what is f at A plus delta x? Well, in the top I have two functions statements I need to find, yeah? And every time I do the function, isn't the function 2 minus something squared? Do you agree? And in the first one, what do I put into the function? A plus delta x. And in the second one, what do I put into the function? Yeah. Right? So the limit as delta x goes to 0 of, let's do this, I guess we'll nibble away at it. 2 minus, what is a plus delta x quantity squared? A squared plus 2a delta x plus delta x squared. All that needs to be subtracted. Minus 2 plus a squared if I distribute the negative. Are you with me? There are some algebra mistakes to be made here. If I then simplify a little more, distributing the negative out front of that parentheses there, it's 2 minus a squared minus 2a delta x minus delta x squared minus 2 plus a squared. Do you agree? What drops out? Subtracts away. The 2 subtract away and the a squared subtract away. In the interest of time, rather than do a rewrite step, what would we do after that? Take out a delta x. Everything left has a delta x, and so if I take away a delta x, or divide out a delta x, what's left? Negative 2a minus a delta x. Can I evaluate the limit now? As delta x goes to 0, this approaches. You know what I should have had in there for a every time is 1. So I guess it's decision time. So I go back and replace all those a's with 1, or shall I do it now? Let's just go, since a is 1 here, the derivative should be negative 2. Yeah, sorry, I should have, instead of a all that time, I should have had 1. Why didn't you see? It's all good. This is not my preference, but it does. What did I find there, label-wise? What is that equal to? Notation-wise, I just found f prime at 1. Let's go graphically and make sure that makes sense. What do you know about the graph of 2 minus x squared? It's a blank parabola opening blank, shifted up 2. All right. It looks like that. Tell me graphically what this means. What do you make out of that statement? At x equal 1, which is probably right here, the tangent slope is negative 2. Does that seem to jive with my picture? All right. Now, that was yesterday's way of finding the slope of the point. We could use this. We could find the same kind of outcome by using a little different approach. If I use the alternate definition, then that means more like look at the difference between f at sum x and f at sum a, and then get x closer to a. It's the idea of Let A be the point you're interested in. Instead of doing this delta x idea, just call x some other point off to the side. And then take x close to A. You follow me? Now in this case then, A is, this time I'm going to get it right. This time we're going to use an x of, or an A of 1. So we want to know what's the limit as x goes to 1 of f of x minus f of 1 over x minus 1. Now let's get into a little more details. What's f of x? 2 minus x squared. What's f of 1? 1 over x minus 1. If I distribute or subtract, I get 1 minus x squared over x minus 1. If I try and evaluate that limit, what do I get? 0 over 0. Now that's always going to happen in derivatives because they're always, if you're trying to go right at and you're trying to find change between a point and itself, so that's 0 over 0. You cannot do that. And so we need to use our limit skills. How do I do a little factoring and canceling here? What's the first kind of problem I have? Instead of 1 minus x squared, I prefer it to be x squared minus 1. So could I take out a negative? And then x squared minus 1, how does it factor? X minus 1, x plus 1. What's the name for that factoring pattern? Difference of squares. X, oops, this is minus, x minus 1 then divides away. That means my 0 over 0 problem just divided away. So what's the limit? Negative 2. Surely then you should get the same answer, and we did. Again, it means the slope of 2. It's just a little different logistics, a little different way of doing it. It should come out the same. Are you with me? Okay. Would you go this, I'll come to it in a second actually. Let's go here. Would you please do example 3 on your own to see if you're getting good at the first definition? After about 30, 45 seconds, I'll write the first step to make sure you're started off. Do feel free to talk over every time when you're doing the club. Your math and English. Here's what I expect. I would expect one of the two first steps actually. Either the most general basic first definition or function specific questions. See what those do. How many of you are a little rusty on binomial expansion? How many of you don't even know what I'm talking about? So this is a binomial because it's two terms. And when you expand it, remember all that Pascal's triangle and all that? Okay. In the interest of time, let's focus on the calculus. The expansion of that is x cubed plus 3x squared delta x plus 3x delta x quantity squared plus delta x quantity cubed plus 1. And then if you distribute negative. Okay. That should get you unstuck. Stop. You should be able to. But if not, Hopefully you saw the x cubed subtracting away and the 1 subtracting away, and then you were able to divide out a delta x, yes? So when you evaluate the limit, what is your derivative? 3x squared, and the label I would attach to that is I just found f prime at x, or of x. That is the derivative rule for all x. All right, cool. Kind of funky. That seems like the squares are always positive or at the least 0, yeah? Do you agree? X cubed plus 1, what does the graph look like? Does that make sense that that would always have positive slope or at the least 0? Math works. All right. Here's the problem. Symmetric definition is the most writing, and I made it on a cube in my infinite wisdom, and that's terrible. And so instead, let's go with f of x is negative. Let's just go negative 3x, okay? Now, obviously, now, because I changed the functions, it's not going to be the same derivative as the first one. That was my intention, is to show you that it's the same, but now that's not going to work. But it'll still be good practice. Now, this is one thing I wanted to tell you, and I forgot to tell you in my notes. Would you jump back up to here? I didn't do it in here, this what it's used to find. Do you agree that in the example I gave you, it was finding f prime at a specific a, but you could use that same idea to find f prime at any x also. So you'll see symmetric, like the first definition. You could use it to find it at a point and you'd see a number in there, or at any x and you'd see x in there. Okay, so in this case, what I'm talking about here is I want you to find the derivative at any x. So that making sure you're getting started right. The idea on symmetric is you take points on either side, a delta x above and a delta x below, and it's 2 delta x's y, and so that's the definition. So would you proceed on with the symmetric definition using that change function of negative 3x? How's it going? Pretty good. I go pretty methodically by my algebra just because I don't want to lose students. I could probably do it in less work. If you did this in a little less work, that's fine. I think you'll see that eventually the x terms drop away, leaving you with delta x is only pretty common. Negative 6 delta x over 2 delta x is negative 3, straight up no delta x's. And so as delta x goes 0, what does negative 3 go to? Well, it doesn't go anywhere, it's negative 3. And so delta x can do whatever the heck it wants. The function is always going to come out negative 3. Tell me why that answer makes sense. Because it's a line, the rate of change of the slope is always the same. What's another word for always the same? Constant. Yeah. Slope is constant. Okay? All right, good deal. let's do some of this a little bit together here, okay? So eventually you're going to want to go backwards. You're going to say, they're going to give you a limit setup, and they're going to say, what are they doing? So, for example, these are all derivatives, and your goal is to say what definition is used, what the function is, and is it f at x, f prime at x, or is it f prime at a certain constant? So for this guy, if you see x approaches 3, anytime you have x approaching a constant, think alternate. So that's the alternate definition. It's not based on a gap shrinking, which is what symmetric and first definition is. And what's the function? Well, in the alternate definition, the top of the derivative is supposed to be f of x minus f of a. So if you want to find f of x, you need to look here and just say, oh, it looks like f of x is what? Absolute value of x. And are they finding the derivative at a number or at any x? At what number? So you're saying that this is finding f prime at wait. Okay? Try the next one on your own. You're giving me 3 things. What definition, what the function is, and at a point or at a new. Okay, so what definition? Alternate, what's the function? And at what point? Great, cool. Let's go to C. Now, H is used in a lot of textbooks as a stand-in of delta x. It's all over the place. It means the same thing. So when you think H, think delta x. So that right away tells me, okay, it's H or the gap approaching 0. So this tells me it's either first definition or symmetric. And then what in here tells me it's not symmetric? Yeah, there's not a 2h here. This is an x minus h here. So it must be the first definition, yeah? What's the function? Well, again, remember this is, in the first definition, it's f of x plus h, which is kind of confusing. But over here, isn't f of x what's subtracted? So you can find f of x by looking at the back end. What's the f of x? X cubed plus 3x. And are they finding f prime at any x or f prime at a certain numerical value? At any x. Okay, cool. All right. Try the next one. Ready? Which definition? Symmetric, excellent. What's the function? X cubed plus 3. I must have done a little cut and paste in here. And what's the at a point or at any x? Try the next one. Actually, just do the next 3, please. When you get those 3 done, get out your calculator for the last part of the lesson. If you don't have one, feel free to phone me. Quickly, by everybody shouting it out. E, what definition? First, or the definition. What's the function? Square root of x. And at a point or at an x? 3. Okay, excellent. F, what definition? First definition. What's the function? 1 over x. And at what? At a point or at any x? Excellent. Last one. What definition? Alternate. X is approaching a numerical value. That's alternate. What's the function? Sine of x. I don't know what to make out of this. There's not a difference out of here. Shouldn't I have two things? Well, what probably was here? Sine of pi. And what is that? Okay. So what is what you're finding? Yeah. Good. Okay, cool. All right, last but not least. So looking at that, what do you reckon that means? It's obviously a limit problem, and we could look at it just as a limit problem. But if we look at it from the lens of today, what is also? It's the alternate definition of f prime at pi over 6, where f is sine of x. Okay? Now, if you try to evaluate that limit, you get a big fat 0 over 0, and algebra's out because sine, doesn't factor and all that stuff. And so normally we would say, all right, let's go to a table. Instead, we're going to have this, for whatever reason, he puts this in now, but your calculator will calculate an estimate of the derivative. Your calculator cannot actually find the derivative of sine. And you guys haven't learned it. Well, last year if you had calculus, you know it, but for the most part, we don't know the derivative of sine yet. So you're going to use our calculator to make a microscopic triangle that gives me a good slope estimate. And I think the Inspire uses a point a millionth away it calculates the slope. It's very close together. And let's be clear, it doesn't know the derivative, it just makes calculations. So this is how you do it. In your calculator, let's just go from the home screen, shall we? We want to find the derivative of sine at pi over 6. You with me on the question? All right. Now, there are a couple different ways to do this based on the way that's not necessarily the least amount of keystrokes, but the least confusing to students. I'm going to go this way. Go to Menu. And what submenu are you going to use? Yeah, you're going to use the Calculus submenu, and you're going to use the numerical derivative at a point, the first thing. The variable is x. You could have functions of time. When we do physics kind of problems, you'll often have t as a variable, but here we have x as our variable. The value is the value at which you want the slope, which is pi over 6. And I totally forgot, there's pi. Pi is there, divided by 6. And for now, you're not going to worry about the first derivative. That's all we know is the first derivative. But you could take derivative after derivative after derivative. But for now, we're just going to hit OK. When it does that, then, it gives you this notation. It's a little cumbersome, but it basically says the derivative with respect to x of what function. Now, here you need to tell the function. You want to say, I want the derivative of sine of x at x equal pi over 6. Hit enter, and there it is, the square root of 3 over 2, or actually 0.866. Now, in terms of what we did there, you said in the scratchpad, basically, you said menu, calculus, submenu, numerical derivative, right? Then we used generally x as the variable. We give the value, which is the a at which you want the slope. And then just choose first derivative. And then OK. And then finally we typed in the function. When it says, what's the derivative of blank at x equal a, you type the function in there and you with me? And so it is approximately 0.866. Do we have time to do that? So try this one real quick. Use your calculator to find the instantaneous rate of change at t equals 6 while p of t is that. Now it's saying t's, but could you? It's not going to know if you just said I'm going to use these x's. Is it going to know? No, that's not cheap. If you want to use x's, that's fine. If you want to use t's, fine. The slope would be the same as a rose by any other name. Anybody have it? Numerical? Give me your 2.880. Okay. Does anybody confirm that? Okay. What did we find their notation was? You should never just have a naked answer. What do we find? P prime at 6. P prime at 6. Okay. Okay. Here's the problem. You have 1 minute to ask questions on 19. Go. Oh, 9 questions? Excellent. Yay. So this happens quite a bit in this class. I don't always have time questions because the lesson takes a while. Different days we'll deal with it differently, but here's today what I'm going to deal with. If you had some problem you just couldn't get or didn't understand, let me know and I will work it at lunch and put it on my feed on my website under yesterday. And you can look at it and get it to me by the end of the day, okay? So shout out if there's anything you want me to work at lunch. 5, 8, 18, 19, 20. Rough patch there, eh? What? 24. That it? Okay. I will put those on at lunch. Also, I don't have first period, so I don't have anybody in my room set up. So if you want to get a pass and come ask questions, fine too. That's cool. You do have to do that code of conduct stuff first, I think. But after that, if you want to come here and ask a question, great. Come see me. Have a great day. Thank you. Is there anything?